Good morning everybody. So, in this class of redox reactions, today we will be basically discussing about three things. First one is the corresponding disproportionation reaction. Second one would be the different redox reactions, how we can balance, because the balancing is always very important in relation to the number of electron getting transferred. And lastly, we will be discussing on the analytical aspect or the application of this redox reaction is the corresponding redox titrations. So, the first thing what we will be seeing today is that disproportionation reaction is a very simple and unique definition we can have for a typical disproportionation reaction is like this, which tells us that disproportionation in a definite type of redox reaction. So, we will be talking something where we are concerned about a particular redox reaction in which the species is simultaneously reduced and oxidized to form two different products. So, if we are talking about the disproportionation reaction of a particular species, we have to think about its corresponding potential in terms of its reduction as well as its oxidation. Such as one such simple example, what we know particularly when we go for heating some inorganic salts. In last two classes what we have seen that some oxides, some carbonates we can heat it with the liberation of oxygen, with the liberation of carbon dioxide. But if we can take the example of a species which is simply a salt of metal is mercury, which is mercurous chloride, where mercury is present in +1 oxidation state. So, one positive oxidation state of mercury giving rise to the mercurous chloride, and a typical reaction condition, because sometimes we have to say it or we have to put some interesting reaction condition such that this reaction goes, which is the UV driven photolysis reaction. That means, the photons are passed through this solid sample and some lysis reaction, lysis means the degradation of the species is taking place and at a particular wavelength which is in the UV region, that means below 350 nanometer, because at this particular energy where the UV energy we are talking about is a high energy, which is energy is higher than that of the visible range. So, that will basically degrade or giving us two products from the degradation of mercury 1 chloride is the mercury, which is 0 mercury, elemental mercury in the liquid form, and mercuric chloride. So, how we can talk about this particular reaction is that if we think that okay, we have from the left hand side to the right hand side, we have basically mercury is present in three different oxidation states. One is in mercury which is in +1 oxidation state, which is mercurous mercury, and on the right hand side after this photolysis reaction we get this mercury as the mercury in the elemental form, that means mercury in the 0 oxidation state, and the oxidized version, oxidized form of mercurous chloride, which is mercury 2 chloride, or we call it as a mercuric chloride. So, what we get that is the typical nomenclature of these ions is that mercurous like ferrous. So, the nomenclature for mercurous tells us that it will be in the lower oxidation state, that means mercury is in 1. So, if we get something, that means if we have some species having some intermediate oxidation state, so that particular species can simultaneously reduced according to this particular definition what is written above, that it can simultaneously be reduced and oxidized. So, one of these mercury in the mercury 1 plus can be reduced to mercury 0 and the other mercury which will be taking that particular electron is giving to the other species will be oxidized to mercury chloride. So, thus we call this as a typical disproportionation reaction. So, this is coming from a metal salt. So, other metal salts also we can have. So, we just simply write that if we have metal salts, so metal salts we can see that Hg2Cl2 is the mercurous chloride having intermediate oxidation state. So, another example we will be talking about, you will see that if you have a copper in again +1 oxidation state, which is cuprous chloride. So, like that of the thing, that means it can have some other thing, it can also happen in aqueous solution or in water medium, that it can go up to copper 0 or it can go down to copper 2 plus, which is also a typical disproportionate reaction what we can follow. So, stabilization of this as copper chloride, and if we think that this is there as cuprous ion in solution which is aqueous. So, in aqueous medium, if we have the cuprous ion, we have to stabilize by some special condition, and sometimes we can take in some non-aqueous medium, that means some solvent which can be CH3CN, which is a commonly known solvent is acetonitrile. Like CH3OH, we know CH3OH is methanol. So, in acetonitrile medium, so this particular ion can be stabilized by forming a complex species which is CH3CN whole 4 plus. So, 4 such solvent molecules with nitrogen lone pairs forming coordinate bond to the copper center, stabilizing this particular species. So, in non-aqueous medium, this can be stabilized, and if we can isolate, like isolating the solid salt, inorganic salt, this can be also isolated in the solid state as a white solid compound, because it is cuprous copper, copper in +1 oxidation state having a electronic configuration of 3d10. So, it is not colored unlike copper 2. So, this is there, but if this particular one is not stable enough in aqueous medium, it can go for disproportion between copper 0, that means metallic copper. So, 50% of the species can be deposited at metallic copper as copper 0, and other half will be going to cupric copper as copper 2 plus. So, these are the relative examples, the typical examples for the disproportionation of metal salts. Similarly, we can have something, that means the elemental states, some species which are in elemental states, say P4, the elemental phosphorus, then S8, that elemental sulfur, and elemental chlorine, the chlorine gas. So, what we see that whether these species can undergo the reaction which we can term as the typical thing, what we are talking about here is the typical disproportionation reaction. So, if that can undergo, we should be able to identify something, that if I say that in a particular reaction condition, because we know that the reaction condition according to the environment of that particular reaction where we are doing, if we are doing that reaction at room temperature, in air, and in condition of the, that means it is in presence of the air and the moisture. So, this is one particular condition. So, there is a possibility that oxygen is also available, and this O2 present in the air can oxidize this particular species, this elemental phosphorus. But if we talk in terms of the corresponding disproportionation reaction, some things would also be available which can in turn reduce the species to some other form. So, the products also we should know very precisely. That is the important thing for knowing this disproportionation reaction. So, from elemental phosphorus, if we get phosphine gas, is a gaseous product. So, is a phosphine gas like that of our formation of ammonia from nitrogen. So, phosphine, which is therefore a reduced form or the reduction product of the elemental phosphorus to phosphine. So, what about the other species? The other species can be the corresponding oxidized form, and this can be some phosphate or phosphide based species. So, is H2PO2 minus. So, is basically the phosphide ion species. So, where you have the phosphorus in the oxidized form from the zero state. So, this particular reaction can take place in basic medium. So, this particular disproportionate reaction, so things are becoming much more complicated compared to that of our UV photolysis of mercurous chloride, where we have seen that simple heating of mercurous chloride can give you two products. But here we should know the corresponding or the typical reaction condition, and also sometimes we do not know, and which is also not very much obvious, that you have the product of pH3 and H2PO2 minus. So, if two products are given, we should be able to write down the second thing that we will be seeing today, which are interrelated in a manner that you should be able to a balanced redox reaction for the reaction of this elemental phosphorus in basic medium to give rise your pH3 and H2PO2 minus. So, that we will see how we can get that. Similarly, for this particular elemental sulfur, so obviously we should know all that elemental sulfur is in zero oxidation state. When it goes for the corresponding reduced form, it can also give rise to some the corresponding species like H2S, that hydrogen sulphide. So, hydrogen sulphide will have a sulphide ion. So, the reduced form is your sulphide ion, and the oxidized form again we just attach oxygen, because you have the available oxygen from the reaction medium in presence of the moisture like water. So, the species containing sulfur oxygen bonds, and in this particular example we will be having S2O3 2 minus, which is the thiosulfate anion. So, thiosulfate anion, what we will be getting is the corresponding oxidized form of the elemental sulfur, while producing the reduced version as sulphide ion. So, these two things again will be producing in the medium by the reaction of again in presence of hydroxide ion or strong alkaline medium, giving rise to another example of your disproportionation reaction. Similarly, the Cl2 also will give rise to two sorts products, again like that of your reduced form of Cl. We all know these will be giving rise to the your chloride ion, and again like that of your phosphorus and sulfur, you simply attach oxygen to the other species. So, will be the oxidized form. So, the electronegative ion, which is the electronegative element which will be attached to chlorine will be ClO, and that ClO minus will be there, and that ClO minus will be again forming from the hydroxide ion medium. So, one will be the reduced form and another will be the oxidized form. So, let us see how these examples, these three examples from the elemental form can be balanced nicely with the help of the balancing terminology, what we just want to say about this corresponding P4. So, you have P4, you have S8 and you have Cl2. So, which can be reacting with hydroxide ion in presence of some more water, and we need 3 hydrogen. So, 3 hydrogens will be there from this hydroxide and 3 water molecules will be there. So, because 3 hydrogens will be required for formation of the pH3 minus, where phosphorus is in -3 oxidation state, here it is in 0 oxidation state, and the other species the number is also twice of that H2PO2 minus, where phosphorus is in +1 oxidation state. Similarly, for this S8 we can have just simply we just look at the number of electron transfer between these species. If it is 1:1, we are fine, but sometimes it is also not 1:1, such as it is accepting 3 electrons and is going to pH 3. So, it is accepting 3 electrons going from 0 to -3. So, this is not always 1:1 type of reaction. So, in the second case, where S8 is reacting with hydroxide ion, giving rise to 4S2 minus plus twice of S2O3 2 minus and 6 molecules of water. And in case of this chloride, the reaction is very simple. Only in the basic medium, we all know that we will be forming the reduced version, which is -1 oxidation state, this is -2 oxidation state, and this is also +2. So, this the chloride ion will be forming along with ClO minus, where this as 1 plus and some amount of water. So, this is typically the hypochlorite solution, or is the common bleach we call, or the Lundy bleach, what can be formed from the reaction medium by reacting this chlorine. So, all other halogens also, like that of our chlorine, we can also go for the reaction with bromine, we can go for the reaction with iodine also. So, similar type of reaction we can follow with that of your bromine, elemental bromine, but elemental iodine. But the tendency for a different type of reaction can be very easily seen from another example what we have discussed earlier, that what about F2, whether F2 can also go for this sort of disproportionation reaction, what the Cl2 then Br2 and I2 is following, but it is not that. So, the F2, the fluorine molecule, does not therefore show up this typical disproportionation reaction. So, this fluorine, which is F20, which is in the gaseous form, when it reacts with the same reagent, the alkali present in the reaction condition, which is in the aqueous form, giving rise to this fluoride will be definitely forming. So, will be giving rise to 2F minus. So, this is twice F2, and this is the unique species what we have discussed earlier, which is a gas also. So, this fluoride will be in the aqueous medium plus H2O. So, this is a typical reaction where we get the fluoride will react in a different form, and this OF2 already we have discussed that you have the F and F like that of our OHH. So, this species will be forming. So, this is 1 minus, this is 1 minus, this is 2 plus. So, what is basically we are getting? So, we are here we are getting phosphorus in the positive oxidation state, sulfur in the positive oxidation state, chlorine, bromine and iodine all in positive oxidation state, but this particular thing, that means this particular element, your fluoride will resist that particular formation, that means it is not forming A plus. So, A plus is not forming in any such reaction. So, it is not a typical disproportionation reaction. So, whatever F minus is forming in the aqueous medium in the gaseous phase, it is again forming OF2, where F is present in the negative oxidation state of 1 minus 1 minus. So, these are the things. So, that means always we know that these F2 molecules, so F2 molecule is the odd element out from this group of halogens from fluorine, chlorine, bromine and iodine. So, it will definitely react in a different manner. So, if we just see from a very simple example of this mercurial chloride what we have seen, and if we just go beyond, that means if we just go beyond for this chlorine, that this particular chlorine what we can see now is the chlorine can assume all other oxidation states in one case also we have seen that it is assuming this 1 minus and 1 minus and 1 plus. So, this particular one can also give you the other oxidation state, because the chlorine can have the oxidation states like +3, +5 and +7. So, other species containing ClO bond can be available for us, which are like that of our ClO minus, ClO2 minus, ClO3 minus and ClO4 minus. So, for assuming all these oxidation states, which are not the sometimes typically the outcome of a simple disproportionation reaction of chlorine gas between chloride and hypochlorite ion, but it can also go further or go beyond. That means, the formation of these as the corresponding chlorite ion ClO2 minus, the chlorate ion the ClO3 minus and perchlorate ion ClO4 minus, where the number of electron transfer will be more than 1. So, while handling this, so basically when we choose this particular reaction or particular aspects of this, where we see that this particular thing is happening where chlorine oxygen bonds are giving rise to more number of oxygen attaching to the central chlorine atom. So, that basically give rise to the different oxidation states of +3, +5 and +7. So, we get that way that this particular one will have, when we handle the chlorine gas, this particular chlorine gas, this just take it out. Okay. So, this one will give you something where when we handle the chlorine bearing some other reagent such as the chlorine gas itself or hydrochloric acid. When we use hydrochloric acid as gas or in aqueous medium, we find that this particular one will give you that something. So, we therefore see that the getting these other oxidation states is very difficult to find out if we do not know the what is the product of that particular reaction when the other species like chlorate and perchlorates are forming. So, the multiple number of electron transfer will be taking place there, and the perchlorate ion we all know when we go for a typical reaction, because this is the corresponding version which is commonly available from acid form, which is your perchloric acid, which is HClO4. So, that perchloric acid containing this chlorine in +7 oxidation state will be highly oxidizing also. So, this particular case also we will see that in another example. So, if we just now we have seen that this particular disproportionation reaction is taking place with only a moderately concentrated sodium hydroxide solution, but if we go for a solution which is dilute one, and in that particular case the reaction stoichiometry is different. So, you see the reaction condition basically changing the reaction stoichiometry. In the previous case, our chlorine is to hydroxide stoichiometry was 1:2, 1 Cl2 was reacting with 2 hydroxide ion, but simple the condition of the reaction, we move from a moderately strong sodium hydroxide solution to a dilute solution, the reaction stoichiometry is still the particular one is forming again is 1:2, but in this particular case the number of electron transfer is of different type, because only one species is forming for a highly oxidized form, that means ClO3 minus the chlorate ion, where you have chlorine is in the +5 oxidation state. Similarly, you can have 0 to +5. So, you require 5 such chloride ions to be formed over there from this reaction as the corresponding chlorate ion. So, this also is all true for a typical reaction in terms of the corresponding interhalogen compound. So, we are talking about the metal salt, the corresponding elemental form of the compound and some other compound which are the interhalogen compound. So, these interhalogen compounds what we see is the BRF. So, when BRF is getting basically in some form, when one Br is attached to F and the stoichiometry is Br and F, but it can go for disproportionation reaction between bromine trifluoride and elemental bromine. So, again we see that is that Br plus and F minus. So, the bromine is present. So, if we think or if we talk in terms of the bromine as the intermediate oxidation state. So, plus 1 it will go to 0 in Br2 and to plus 3 in BrF3. So, which is also true for typical example of some other compounds which are typical interhalogen compounds. So, similarly, we see that simple other gas compounds. So, gases also have some tendency, if we know that these gases, because most of these gases which are oxides, the nitrogen oxides, the sulfur oxides, we all know that these oxides are basically anhydrides of the corresponding acids or the mineral acids. So, nitrogen dioxide is also a corresponding anhydride of the corresponding acids, but this NO2 which has a typical oxidation state of plus 4 and it can react with water going for a typical disproportionation reaction. That means, the plus 4 oxidation state of nitrogen dioxide is not very much stable in this particular form. So, it is not very much stable to give us some other species or the corresponding compound, that means the corresponding hydrated form. So, that hydrated form we are not getting at the corresponding acid, and that acid basically we are getting when we react this NO2 to H2O is the corresponding nitrous acid. So, nitrous acid is, if we just to quickly look at the corresponding oxidation state of this nitrogen over here. So, its O2 is 2 to 4 and hydrogen is 1. So, 4 minus 1 is 3. So, negative 3 is there. So, nitrogen is plus 3. Similarly, this nitrogen is also 3 into 2 6 plus 1 is 5. So, it is plus 5. So, this plus 5 and plus 3. So, the plus 4 oxidation state of nitrogen in nitrogen dioxide will prone to disproportionation reaction between plus 3 and plus 5. So, when it reacts with water, because it will be disproportionated for different oxide or the oxygen ions, it is not that it will disproportionate into two other gases, because we all know the nitrogen can give rise to other oxygen gases like nitrous oxide, then N2O3 and N2O5, all like this. But since the reaction is taking place in presence of water, so it will be forming two acids, one is nitric acid and another is your nitrous acid. So, before going to these redox titration reactions, so we will be just quickly see the corresponding thing, that means how the different redox reactions, because we will be utilizing those redox reactions for those redox titration is the balancing. So, if we just simply consider that the balancing, and one such example, because always we take the direct laboratory examples, or the experimental chemistry is always nice in knowing all these things. So, laboratory chemistry will also help us into knowing a species which is oxidant. So, which is typically labeled as the oxidant, which is your dichromate ion Cr2O7 2 minus, and we will give you some condition for this particular reaction, which is the acidic condition, that we give acid to it, or the medium is acidic such that will prevent in reacting with water itself or hydroxide ion formed from this water molecule. So, it will be faintly acidic or feebly acidic or slightly acidic, which reacts with SO3 2 minus, the sulphide ion. So, this is your oxidant, this is your reductant. What is happening and what sort of reaction we can expect? So, we should also know, so these are the reagents. So, if this is A and this is B, we get this reaction to C plus D. So, identification of all these are important. That means, we should know what is A, we should know what is B. So, the correct assignment of the formula of each compound, that means which are reacting A and B, and the products also C and D. So, since this is oxidant, since this is reductant, so this oxidant will be reduced. So, if this is your oxidant and this is your reductant, So, this oxidant will be reduced. So, what are the reduced form of this? Chromium is present in +6, which is hexavalent chromium in dichromate. So, hexavalent chromium will be reduced down. It can go to +5, it can go to +4, it can go to +3, but which is most stable one and which is very much stable in this particular reaction condition, which is slightly acidic. So, in this particular condition, C will be your chromium 3 plus, the chromium 3 ion. So, it will be reduced to chromium 3 plus ion. What about this reductant, that means the reducing agent which is responsible for the reduction of this dichromate species? So, any other chromium anion or chromium species based on the +6 oxidation state will be reduced by this reagent, which is nothing but the corresponding species, which is, this is oxidizing as oxide, the sulfur trioxide, but sulfur dioxide is the reducing gas. When it reacts with water, we get sulfurous acid, and that sulfurous acid, when it is ionized, we get the corresponding ion as the sulphite ion. So, sulphite ion, which can also be produced from the metabisulfite, which is the anhydride of this sulphate. So, this is the reducing agent. So, this species will be reducing. So, if we just simply have a solution, so orange colored solution, you can have aqueous solution which is slightly acidic, and you pass sulfur dioxide gas, the same reaction can happen over there. So, this thing is there. So, the reductant, that means this species should be oxidized. So, SO3 2 minus should be oxidized. That means, in other way, if we consider it that SO3 2 minus will be oxidized by this oxidizing agent, which is your dichromate, because the commonly used salt we use in the laboratory is the potassium dichromate solution. So, a solution of potassium dichromate can be able to oxidize your solution which is containing sulphide, and sulphide we know that this is in +4 oxidation state will be oxidized to sulphate, which is in +6 oxidation state. So, that gives rise to the assignment of this thing. So, the correct assignment of the reagents and the products, that means the assigning A, assigning B, assigning C and assigning D is also important. Then next step, the assignment of the corresponding oxidation states. What we have seen that the species what is forming, where it is. So, it is in +3 oxidation state, +6, it was in +4 and it was in +6. So, then the total number of electron transfer what is taking place over there, that we also try to find out. So, here the number of electron transfer is basically what we get if you have chromium in the hexavalent state to a trivalent state transfer is giving to for 3 electron acceptance or 3 electron reduction step. Since we have 2 chromium centers present itself in the same species, that means the dichromate anion. So, total number of electron transfer will be 3 plus 3 will be 6. So, we have 6 electron transfer for this step. What about this for the sulphide to sulphate conversion? So, sulphide to sulphate conversion is 2 electron transfer reaction. So, this is the thing, that means the imbalance in the number of electron transfer between oxidant and reductant, that has to be matched. So, the increase in decrease in oxidation number. So, the third step would be the calculation of the increase and decrease in the corresponding oxidation number per element species or per atom of chromium or per atom of sulfur. Then we just go for the total ionic charge balance, because the ionic charge balance is also important, because what we should use, that if the medium is alkaline we should use water if the charge is not required, but if the corresponding charge is required we should be using hydroxide ion. But if we require the cationic charge we will be using it as H plus, and the product of this, because these two we combination of this reaction or elimination of this O minus or addition of O to this sulfur center will just either consume water molecule or produce water molecules. So, addition of water molecules will also be there, and balancing the hydrogen atoms from the left hand side to the right hand side will give rise to this particular reaction. So, what in essence, so if we sum up this particular reaction, what we will be getting over there for summing up this reaction, simply that Cr2O7 2 minus will be there, for balancing the total number of electrons. So, it will be 3 into 2. So, we have 3 SO3 2 minus forming 2 Cr3 plus and 3 of the sulfate ions. So, that basically and critically matching the number of electron transfer reaction for this. So, more number of examples we can have, and we can have several others. So, quickly we should see some of these examples of these balancing reactions, because we see for the redox titration. So, if we have the nitric acid, which is the most common reagents which we deal with in the laboratory in your general chemistry textbook as well as in the experimental part. So, when nitric acid is getting reduced by H2S, we have the nitric oxide and the elemental sulfur. So, this is a very precise example of sulfur is going from -2 to 0. So, you have a change of +2, and this nitrogen is changing from +5 in nitric acid to +2 in nitrogen. So, it is -3. So, the multiplication will be in terms of this 2:3. So, the reaction will go like this: twice of HNO3 plus thrice of H2S will be giving rise to the liberation of nitric oxide, which is a very interesting molecule. We should also study when we study the nitrogen chemistry in the group, that the oxide of nitrogen, or when we study oxygen in the group, that oxides, because it is a very interesting molecule and is a very biologically it is also very important, and is for the detection purpose also. The identification of the nitrates and nitrites will also be detected by the presence of or the liberation of this NO. So, this NO and the elemental sulfur. The sulfur is in elemental form, is the corresponding powder form, as very small particles will be forming, and that is in the 0 oxidation state, and that will be floating around. So, elemental sulfur liberation will also can take place, and that is also an interesting observation in the laboratory chemistry or experimental chemistry or practical chemistry, is that you can see this elimination of sulfur from that particular reaction. So, another interesting species or the reagent is like that of your potassium dichromate is your potassium permanganate KMnO4, where manganese is present in +7 oxidation state, and if that particular one is reacting with simple a chloride salt, because the chloride salt all we know how we can identify. So, if any of them can be your unknown species in the laboratory experiments, also how we can identify this. So, we will be taking the help of again a particular redox reaction, and that redox reaction, if we know that it will be going for some reaction where Cl2 is forming, that means chlorine is in 1- oxidation state, will be going to chlorine 0. So, that chlorine 0 formation is basically is corresponding oxidation reaction. So, any chloride salt, this is potassium chloride salt, even for hydrochloric acid, which is HCl in aqueous medium, which has also chloride as 1-. So, that can be oxidized, and this is our oxidizing agent. So, KMnO4 may be in solution, we should know the corresponding reaction condition, or in the powder form. If we add drop wise this KCl to this particular powderic form of this KMnO4, we will be able to get chlorine, and this gas, once it is formed, we take out from the corresponding flux, the reaction flux we can have. So, the reaction flux we get. So, from that we get and collect this particular Cl2. So, Cl2 will be forming. So, this is also a typical example for Cl2 preparation. So, this Cl2 is giving. So, what about this manganese then? So, this is very simple, that chlorine is going from this to this, that means it is -1 to 0. So, once level of oxidation change, that means +1 change, but the manganese in this particular condition, which is not alkaline and which is not neutral, if it is slightly acidic, because this reaction can take place in slightly acidic or almost very close to neutral condition, that it will form manganese in the manganese ion. So, it will be forming the corresponding salt as manganese sulphate. So, if we add some acid to maintain the reaction condition, acid of our choice would be, therefore, since the sulphate we are writing here will be your H2SO4. So, in presence of that sulphuric acid, KCl will be oxidized to give rise to some reaction where this KMnO4 will be utilized for its oxidizing power for the production of chlorine gas. So, the balanced equation, so the balanced redox reaction, so balanced redox reactions what we can have for this is this therefore KMnO4. So, twice of KMnO4 because this balance is that is 7 to plus 2. So, this is plus 2. So, this will be the change in minus 5 and here this change in is also plus 1. So, the reaction stoichiometry will be 1:5 and since this is the corresponding doubling of this Cl2 is there for the chlorine gas elimination, it will be again doubled. So, it will be twice of KMnO4 instead of 1 KMnO4 twice of KMnO4 because we will be taking there 5 into 2 of 10 of KCl in presence of 8 molecules of sulfuric acid which is typically balanced because the balancing the proton, balancing the sulfate anion, all these things in the different steps like 1, 2, 3, 4, 5 what we just discussed will be following for the formation of the corresponding MnSO4 which will be forming 5 times of that chlorine and along with that because this cation is there and this anion is there which is in excess and some other thing is also in excess is the corresponding hydrogen ions and the oxygen what is coming from this permanganate is the formation of water. So, these are the byproducts or the side products of the reaction is your K2SO4 potassium sulphate and water molecule and balancing this thing will be giving you 8 water molecules will be forming along with 6 K2SO4. So, we get something where we can see that the balancing is important and we can have some typical other examples we can work out and we can also jot down these reactions for typical other species where we get and I will just give you some examples where we can have some species like CuS, the reactions of CuS with HNO3. We should follow the reaction, we should know the reaction and how the reaction goes and ultimately the balanced redox reactions we should be able to write in terms of the number of electron transfer between the oxidants and the reductants. So, cupric sulfide we know that it can be precipitated in the group separation table in analytical chemistry or the inorganic chemistry practical classes and is just can be dissolved in nitric acid. Similarly, one typical example of AS2S5 which can also be oxidized by this oxidizing agent which can also fulfill something else that it is oxidizing agent at as well as it is maintaining the corresponding proton concentration in the medium. So, what is forming over there from this particular one case that means whether we are getting some arsenate ion or not that is important and whether we are getting sulfate ions from there or not that is important. So, these reactions will tell us these products we should know the follow up of these reactions in a fashion like this. Similarly, we can have CH3 PO4 whole 2 which can be reduced by coke or charcoal or carbon. That means carbon reduction process which is a typical industrial process we know that charcoal or carbon reduction process. So, that is the reduction process and it is also the reductant and in presence of SiO2 which will be forming something where we get that is the corresponding formation of the species like that, that means the silica which it can be converted to the silicate to take out some species from this reaction condition. So, this basically give us something where we can consider this as the corresponding preparation of P4 the elemental phosphorus from phosphate rocks. So, this is the rock species. The rock species can be reduced to form some value added species or value added product is the preparation of the elemental phosphorus. So, these are some examples. So, one such example is that the handling some more complex inorganic compound is potassium ferricyanide. Handling potassium ferricyanide and how the redox chemistry goes with potassium ferricyanide we should also know and this when react with Cr2O3, the chromium and the chromium oxide in +3 oxidation state. So, assigning this and assigning the corresponding oxidation state of this iron center, and if we know the corresponding products which will be K4 FeCN6, which is this is ferricyanide, this is ferrocyanide, which is iron in the +3 oxidation state, this is iron in the +2 oxidation state, and that ferricyanide is behaving as an oxidizing agent for the chromium oxide, which is in the lower oxidation state of +6 and which will be oxidized to chromate. So, this will be forming CrO4 2 minus, and this particular species we all know is stable in alkaline medium. So, the reaction will go in presence of hydroxide ion. So, we know A, B, C, D, we know the reaction medium. So, we know the number of electron transfer, we can follow the number of electron transfer for this reaction. So, we can write the balanced redox reactions out of this. So, now quickly we should see that how these balanced redox reactions can be helpful for our redox titrations. So, redox titrations are utilization of the corresponding redox reactions basically for this particular thing, that means how we can handle a particular redox reaction for titration purpose. Titration means how you can understand, how we can find out the unknown concentration. It is not only in the domain of chemistry, it can go to biochemistry or any other area, that where we can quantitatively utilize the redox titration or the redox reaction to understand or to find out any unknown quantity in any sample. So, is the another branch of chemistry is opened up using this particular one is the analytical chemistry branch. So, what this we will be utilizing the redox reactions and for quantitative analysis, because we know that something we call as a qualitative analysis, that means the identification of the species, such that chromium in any unknown sample, chromium in still, chromium in ore or chromium in any other material can be identified first. That means whether chromium is present or not. That is the aspect what we call as the qualitative analysis. Now, the next stage of knowledge or next stage of understanding or next stage of information what we can have is that how much chromium is present in that particular species. So, the amount present will be known by knowing the corresponding methodology where we find or where we analyze the sample quantitatively, and one such procedure is by doing redox titrations. So, these titrations also involve therefore the reactions between oxidizing and reducing, the way we are just now we have seen while balancing the redox reactions, which will help in understanding or knowing or estimating the amount of unknown substance. This is important, this term is important. Unknown substance in any solid sample, any biological sample, any biochemistry sample, any geochemistry sample, any other sample in this universe, which can be having some composition element wise. That means same chromium is present, it can be in your precious stone also, in gem. So, that chromium can be identified. One thing is that since we do all these redox titrations in the solution medium, the substance, the material can be taken into the solution, that the solution preparation would be very much important for all these cases. So, these are the techniques. So, the techniques are very important, and therefore, since we are utilizing for these redox titrations the reagents, that reagent what is we are talking as that, since we are talking that oxidizing and the reducing agent. So, we can use oxidizing and reducing agent. So, definitely if we use some oxidizing agent, say some reagent we will be utilizing is as the oxidizing agent. So, potassium permanganate will be utilizing. So, just now we have written some reaction that potassium permanganate can be useful for the generation of chlorine gas. So, the same potassium permanganate can be utilized as oxidant in redox titration to analyze the other unknown species, the unknown species which we call as analyte, the analyte will be identified, or the amount of this unknown species can be identified by knowing its reaction with KMnO4, which is your oxidant. So, this particular analyte should be your reducing agent. So, which can be oxidized by KMnO4. So, utilization of this KMnO4 as oxidant for redox titrations has a special meaning. So, any other species which can be oxidized by KMnO4 will be utilized for this particular titration. So, the name of this thing is therefore your redox titration based on KMnO4. That means the permanganometry, the permanganate, potassium permanganate we are using for some titrimetric analysis, which is therefore a permanganometry. Metry is therefore the metric arrangement, the metric analysis. So, there are other examples of oxidizing agents. So, one we just now we have seen the corresponding balanced equation based on the dichromate ion, which is K2Cr2O7. So, when you use K2Cr2O7, which is nothing but your potassium dichromate. So, the inherent species which is there already in that particular compound, 2 chromium centers are present, which is bridged by 1 oxygen. So, chromium centers we cannot take out from there. So, is the dichromate itself can be utilizing for that particular oxidizing agent, because it has a specific E0 value, and once we know that the amount of its oxidizing ability, we can choose the corresponding reducing agents or the reducing analyte, which is getting reduced by doing the titration, whether we do it by permanganometry or dichromometry. Similarly, we can have the ceric ammonium sulphate or ceric sulphate, which is a double salt like more salt. So, we call it as a cerimetry. So, this cerium sulphate can be utilized, and this iodine can be utilized in 2 such titration, 2 such redox titrations are well known, and one is therefore the corresponding iodometry, where iodine can be liberated from the medium from say potassium iodide, and that iodine can be the corresponding amount of iodine can be estimated by the corresponding titrimetric method, which is known as iodometry. And iodometry is a different type of thing, where you have a standard solution of iodine in the burette, we take that in burette, and we go for that particular iodine as the oxidizing agent to titrate the corresponding reducing substrate in the conical flask. So, why we are having these examples, that means 1, 2, 3, 4 examples for these redox titrations. Why we are taking so many of them? Because their E0 values are different. One of them can be highly oxidizing and the other is not. The KMnO4 is the strongest possible oxidizing agent among all these, and if we consider this as having a E0 value of 1.51 volt, so this E0 value will immediately tell us where the I2 value is 0.51 only. So, this particular one is weakly oxidizing and KMnO4 is strongly oxidizing. So, we can have under the category of KMnO4 we have series of compounds which can be analyzed. Similarly, using potassium dichromate we can analyze some other compounds from there. So, this is therefore a powerful oxidant. KMnO4 will be a powerful oxidant, and which is used quite often and in acidic condition. So, in acidic condition, this particular E0 value for the half cell reaction between MnO4 minus and Mn2 plus, that means manganese in +7 oxidation state and manganese in the bivalent state, will giving rise to a E0 value of 0.51 volt, and which is highly colored, because the permanganate we know because of this charge transfer transitions. Manganese, though it has no d electron, is a D0 system. Manganese is in +7 oxidation state, but due to charge transfer transition it is violet in color. So, this violet color will disappear during titration. That means, the disappearance of the color during the titration, we can follow this reaction from the corresponding reduction of MnO4 minus to Mn2 plus, which is a colorless one. Therefore, we do not use any indicator to indicate the end point of that particular titration. So, to indicate the redox titration where the reaction is completed, that means, the reaction has gone 100%, almost 100% towards right, where no more this reducing agent is present, because all these 5 electrons will be transferred to the other species, which will be accepting these 5 electrons quantitatively for its oxidation by MnO4 minus. This particular potassium permanganate is not a primary standard, so it has another problem because it has trace amount of MnO2 because it can undergo some self decomposition reaction. Because this MnO4 is stable in acidic condition, but when we preserve in the neutral condition in water solution, some amount of this MnO2 is forming where manganese is reduced only to manganese in the +4 oxidation state, and if the water is not very much pure, it has some organic impurity, and that organic impurity can function as the item which can be nicely oxidized by KMnO4, and that KMnO4 will be degraded to forming some MnO4 in the medium. So, invariably some amount of MnO2 is present. That means, some amount of KMnO4 will be lost and some amount of MnO2 will be formed in the reaction medium. So, this particular one we call it as the primary standard, and that primary standard thing can be titrated by some other primary. This is not a primary standard, therefore, it is a secondary standard solution, and which can be standardized by titrating with standard solution of either oxalic acid or sodium oxalate. So, this is sodium oxalate which can be nicely oxidized by KMnO4, and this is the corresponding balanced equation for that redox reaction between KMnO4 and oxalic acid, and that KMnO4 oxalic acid, because oxalic acid after oxidation giving rise to formation of this only carbon dioxide, and this manganese will be again like that of the previous example of the half cell reaction is that reduced to manganese sulphate only, and this particular reaction. So, quantitatively if we know, since this sodium oxalate solution is a primary standard solution, so knowing the strength of this sodium oxalate solution, we will be knowing the corresponding strength of the secondary standard of KMnO4, and immediately before performing the actual titration we find out this strength and we use it for estimating some other species. So, this is the standardization process. So, this standardization process can be utilized for the formation of different thing. That means, if we have some unknown strength of hydrogen peroxide, often we use from any laboratory we use, because this is not a very stable quantity even if we preserve in solution in under refrigerated condition, but when we use it we should know the actual strength of hydrogen peroxide what we can have. So, knowing of this actual strength of hydrogen peroxide, we have to use the corresponding balanced redox reaction of KMnO4 with hydrogen peroxide, and that KMnO4 and hydrogen peroxide reaction will definitely be giving rise to again the manganese sulphate, and this hydrogen peroxide will be oxidized. Now, the same example what we are knowing from the very first day of these classes, that we will be going to the production of dioxygen molecule. Similarly, the determination of sodium nitrite, we all know that sodium nitrite, when we dissolve it in any acid such as sulfuric acid forming nitrous acid. So, the identification of the amount of sodium nitrite or the amount of nitrous acid in the reaction medium can again be found out by quantitative titration, the redox titration by means of potassium permanganate, and this nitrous acid will be oxidized to nitric acid. And the third one is a very nice example where the iron in the ferrous sample, that is very important, because the ferrous sample is not always very easy to get, because ferrous sulphate itself is not stable in the laboratory condition, only in the highly pure form in the crystalline form, and it is stabilized in a double salt which is known as ferrous ammonium sulphate or ferrous sulphate ammonium sulphate double salt, which is known as Morse salt. So, when Morse salt is dissolved in water, we get the active species which can be oxidized by KMnO4 is your ferrous sulphate. So, that ferrous sulphate can also be estimated by permanganometry by titrating it with KMnO4 solution, standard KMnO4 solution, which has been standardized by standard sodium oxalate solution in presence of sulfuric acid to give this particular one, and the unknown concentration of this, that means the ferrous sulphate solution, can be found out from these reaction stoichiometry and the balance reaction and the mole reactions. So, this particular case, the ferrous sulphate, the amount of ferrous sulphate. So, any other sample of iron also, the simple thing is that any iron sample, if you transform this, because we know that from iron nail to iron sheet, we know how to convert that iron sheet or iron nail to ferrous sulphate. So, that can be converted to ferrous sulphate, and that ferrous sulphate can be titrated or estimated by knowing its titration with potassium permanganate. So, lastly, we will just conclude over here that how we get this the reverse reaction, because potassium permanganate we are utilizing for the formation of the corresponding KMnO4, but how the reverse reaction, that means the oxidation of Mn2 plus can be achieved for the formation of MnO4 minus, and this is a typical introduction of another oxidizing agent, which is your sodium bismuthate. So, you have two step of reaction, that means the oxidation of Mn2 plus and reduction of bismuthate ion BiO3 minus to bismuth 3 plus, giving rise to two half cell reactions, and those two reactions when we sum up in this form where Mn2 plus is available. So, any manganese 2 plus we can have. So, any manganese 2 salt, whether it is a manganese ion in as chloride salt, so manganese chloride or manganese sulphate. So, what we get, sodium bismuthate is the standard reducing agent, oxidizing agent in the laboratory, which can immediately oxidize this manganese quantitatively to the permanganate. So, once this permanganate ion MnO4 minus ion is formed in the medium, we see by the color change simply, because it is the violet coloration will take place over there, that means the Mn2 plus has been converted to MnO4 minus. So, this is giving rise to some identification of Mn2 plus. So, how you identify Mn2 plus in any unknown sample? So, this is the test that you use sodium bismuthate, and sodium bismuthate oxidation will convert it to this, and you can identify by knowing the color. Then how much it is forming, you get that quantitative transformation this, and you estimate the particular potassium permanganate or MnO4 minus what is formed over there by titrating with sodium oxalate. And all these reactions are taking place in acidic medium, and hydrogen ions and water are added to these half reactions to balance the corresponding overall reaction. So, this overall reaction we have to balance, because we are utilizing 14H plus and forming 7H2O. So, like that of our reaction of MnO4, because MnO4 minus is very much stable in acidic condition. So, the formation of MnO4 minus is also in the acidic condition. So, that is another example of this, that MnO4 minus and Mn2 plus whatever we are handling for this quantitative estimation, that means the laboratory chemistry or the theoretical chemistry, what we can understand by knowing the reaction, the balancing of all these reaction is in acidic medium. So, this is purely we are having in the acidic medium, but what we get in that corresponding one in the reaction what we can have for the sulphate, what we have discussed earlier. So, this is basically a reaction where we can utilize in basic medium. So, this potassium permanganate is directly going to Mn2 plus, this is due to the corresponding medium, the acidic medium. So, acidic medium is therefore very important if we go for a corresponding redox titration reactions, but if we are able to get some reaction in basic medium. So, basic medium in that way is not very much helpful. When you use this simple reaction, we are not writing any HO minus for its basic medium, but we are writing simply H2O. So, because this H2O will be consumed for the formation of more amount of KOH. So, the medium is basic in that way by formation of KOH from left to right. So, this is getting converted to MnO2, and that MnO2 what we are getting is not soluble in the aqueous medium. This will be insoluble in aqueous medium. So, that will be liberated out. So, this reaction is therefore not helpful for any such permanganometric titration. So, all permanganometric titration, likewise the dichromometry also is helpful to doing it in the acidic medium only. So, in the basic medium this will be precipitated out, and we cannot do or we cannot perform the corresponding redox titration reaction. So, as a result what we can state that in basic medium the hydroxide and waters will be added for the balancing the reaction, and the half reactions will be there to balance the overall reaction. And this overall reaction is very important, and this overall reaction once we get and once we have the understanding where you use. So, this reaction we cannot use for the corresponding titrimetric method of redox titration utilizing KMnO4. It will be only utilized for the oxidation of sulphide. Similarly, some other species will also be available over there, which can be utilized for the use of this KMnO for this oxidation reaction. So, this is some example only based on KMnO4. Likewise, we can use ferric sulfate, we can use iodine. So, these are the techniques where we can use. So, one such example we have discussed, that KMnO4 can be utilized for typical redox titrations in analytical chemistry. Okay, thank you very much.